Hi, I'm Zor. Welcome to Unizor Education. We continue talking about laws of Newton, and in particular we will talk about today about how planets are basically moving around our sun. So the first person who kind of came up with certain formulas, or at least mathematical description of the orbits, was Johann Kepler. He lived in around 1600, and he came up with the so-called first Kepler's law that all the planets are moving on elliptical orbits, with Sun being in one of the two foci of this ellipse. He came up with this particular statement experimentally. So he was basically observing how planets are moving, and well, that's basically his conclusion. Today we will try to come to the same conclusion purely theoretically, based on certain laws of physics which we already know, and certain mathematical apparatus which we addressed before, like what is ellipse or hyperbola or parabola, whatever. Okay, so this lecture is called Kepler's first law. It's part of the course called Physics Plus for all. It's presented on unizor.com. So if you will go to unizor.com, you have to choose the course called Physics Plus for all, and there is a menu, obviously. So the first level you will choose laws of Newton, and then you will have another set of lectures, and one of them is the Kepler's first law. Now, all the lectures have very detailed description, like textbook basically, and whatever I'm talking right now is presented in writing at the same place, on the same web page. You have the video on the left and the notes on the right. Okay, and the website is totally free. You don't even have to sign on unless you're studying under somebody's supervision. And there are some other courses like Math for Teens, Physics for Teens, Math for All, and Physics Math Plus for All, and Physics Plus for All, and some others. Okay, so let's get back to first Kepler's law. Okay, now the theoretical basis for our today's calculations and derivations are two major laws, which are basically the foundation of physics, classics physics. It's the Newton's second law, which in a very, very primitive form looks like this. Force is equal to mass times acceleration. And again, Newton's another law, the universal law of gravitation, which basically tells that if you have two different objects of two different masses, then the force of gravitation between them can be expressed as this type of a formula, and the direction of this force is on a line connecting these two masses at any point. Now, this is again a little simplified, I would say, presentation of these laws. In the reality, you have to remember that we live in a three-dimensional world, and things like position, force, acceleration, they're all vectors. So today we will use these, but I will present them in the vector form to basically to use in our case. Now, the first thing which I would like to remind you is in one of the previous lectures, I think the lecture is called Planet Orbits. We were talking about the fact that the orbit of any kind of an object in the central gravitational field is a flat curve. So whenever in the very beginning of motion, let's say at time equal to 0, whatever we choose as a time is equal to 0, you have position, you have velocity, so it's a vector r and velocity vector v in any kind of a coordinate system. So you have position, which is basically the direction from the origin of coordinates. This is vector r. And you have velocity of this. Then these two vectors define a plane, basically. And whatever this plane in the very beginning is established, then all the future direction will be within the same plane. Now, why is that? That's actually very simple. Because the source of the gravitation is usually in our origin of coordinates. So, considering that the direction of the force of gravitation between the source of gravitation and our object is always on the line which connects them, there is no torque. There is no any kind of force which will bring them outside of this plane. And mathematically, I did prove it in this lecture, which I just told about, the planet orbits. Okay, so basically, if in the very beginning we choose a coordinate system with the origin at the place where our source of gravitation is, let's say it's the sun, for example, and our object is at some point at time t is equal to 0, and there is a initial position, obviously, so there is initial position r of 0, and there is initial velocity if they are given to us, then basically it defines the whole plane where the motion actually occurs. And we can choose this plane as xy plane. And from now on, I can consider that xy plane is defined by these two vectors. And I know that all the future movement will be within this plane. So if this is xy plane and movement in this particular plane throughout the motion, then obviously the z coordinates is equal to 0. Z coordinates of vector of position and obviously z coordinates of the velocity, they're all having z coordinates equal to 0. Everything happens in the xy plane defined by these two vectors in the origin of coordinates, which is the source of gravitation. So we have the system of coordinates, we have the source of gravitation at 0 in the origin, and we have plane defined by these two vectors. So we're not going to talk about where exactly everything happens. It happens within this particular plane, which means coordinates x and y of our object are variable which depend on time. Okay. So far so good. What's next? Well, next we are actually ready to write equations of motion. So equations of motion are based on these two things. So let's just express all these in vector form. So the first is force as a vector is equal to mass times acceleration. Now, the force will be function of time. Acceleration is function of time. Now, why the force is is the function of time? Well, because the object is moving, and with its move, there is a different distance from the source of gravitation. So obviously the vector is changing, and acceleration vector is also changing. But again, what's very important is that force and therefore acceleration are always directed between the source of the gravitation and the object, which means vector of force is collinear with vector of acceleration. I'll put it as t, and collinear with position vector. So these are all on the same line between object and the source of gravitation, and zero basically. Okay? So that's very important now. So let's first consider these two things. Now, if r is basically x and y, then v vector is x prime of and y prime of t. So the speed is the first derivative. So velocity as a vector has coordinates which are first derivatives. And acceleration is derivatives of, okay, I'll do it this way. It's the second derivative of position. So this is basically definitions of, in mechanics, what exactly is the speed or velocity as a vector, or what's acceleration. So the velocity is the first derivative and acceleration is the second derivative. So I consider this as a known given, and we're not going to talk about this a lot, but it allows us to do this type of equation. So m times a of t as a vector now is equal to this vector, which is g times m divided by r square. But here this is not a vector on the right. On the left we have a vector, on the right we don't have a vector. So I would like to have the vector here. So how can I do it? Well, r by itself, without the vector, r is basically square root of x square of t plus y square of t. That's the length of my position vector, right? It's Pythagorean theorem, very simple. So this is not, again, this is not a vector. R square is x square plus y square. R square of t is equal to x square plus y square of t. But I need the vector on the left. So how can I have this vector? I'll do it very simply. I will multiply it by vector r, and I divide it by the length of vector r. So it will be r cubed. So this r is the length. R of t is equal to length of vector of r of t. Okay? So if I multiply it, it means my direction will be the same, right? They're all collinear to each other. But since I changed the length, the magnitude of this vector, by r, I divide it by r. So this is basically the same thing. And this is our equation, which basically defines the motion of the object in the gravitational field. Now, what's interesting is if you will basically change it into x and y coordinates, then instead of a of t you can put x second derivative y second derivative of t, and instead of r you can put x and y, vector x of t, y of t. So this is a vector equation, not just vector equation, it's a vector differential equation. So which means that m times this is equal to g m divided by what? square root of x squared plus y squared cube times x of t. And the same thing for y, basically. Y, second derivative, it will be y here. So that's what it means. It's a vector form, and this is just bi-coordinate form. All we need is to solve this equation, this differential equation. It will, considering it's second degree, it will depend on two different constants, and we do have certain initial conditions. So we have x of 0 and y of 0, and x prime, first derivative of 0, and y prime of 0. So these two conditions, it's actually four conditions because it's a vector, two of these and two of these, they would define whatever is necessary for making our solution basically dependent on these initial conditions. Depending on position and this and the velocity of our object in the very beginning, the whole trajectory will depend. And now, I mean, if you just think about it, if the velocity is not very high, then most likely our source of gravitation will not let this particular object go anywhere else. It will somehow move around the source of gravitation. Well, on elliptical orbit, yes, we will see it. Now, if the source, if the object moves faster, it might actually move so fast that the force of gravitation will not basically hold it in its own neighborhood, but it will definitely change the trajectory. It will just turn it a little bit towards itself, but then the object would still fly away, and that would be most likely it will be hyperbola of trajectory or parabola. But that we will see at the very end of this lecture, that it will be one of these second order curves. So far we know only this differential equation. The problem is it's not easy to solve. And the rest of this lecture I will basically talk about how to derive certain characteristics of the trajectory without explicitly solving this particular equation, or a little bit solving, let's put it this way. Okay, now I would like to make the whole thing like simpler, and maybe that would allow me to come up with some solution. So the result of research of many different people during many different times, starting from Newton, actually prompts us to not only consider this Cartesian coordinate system where x and y participate, but also the polar system of coordinates. And it would be simpler just because of that. I mean, there is no other reason, just simplicity. And even that is not really so simple. So what kind of a polar coordinate we will use? Well, obviously the origin will be in the same place as origin of our Cartesian system. We are talking about the plane where the whole motion is occurring. So the z-coordinate would be 0 so far for all kinds of components we have here. So, the angle, so if you have a plane, you have 0, this is x, this is y. So our object at point 0 is considered to be at some point, and we have chosen the x coordinate to basically coincide with the initial position of the object. So this is our object at time 0, and then it moves somewhere else, whatever it moves. This would be at position at time t. So the angle, we will obviously count theta from OX to OP. So we have an angle, and the distance from O to P, that will be our R. r of t, sorry. R of t. This is the distance. And obviously you can consider vector r of t, which is this vector, OP. So we have an angle and we have the length. Basically, if you're talking about flat curve on the plane, if you have the length from origin to a point as a function of angle theta from OX to direction of P, that would be sufficient actually to define the curve itself. And again, in the lectures which were dedicated to second order curve, which is a previous lecture actually on this course, where I also referred to mathematical lecture dedicated to all the curves of the second order. We do have an equation of ellipse, parabola, and hyperbola in this polar coordinate form. So what I'm going to do, I'm going to derive equation of trajectory in this form, and it will basically be the same as equations for second order curves, for ellipse, hyperbola, and parabola. So that's my goal. Okay, now all the details of the calculations are, as I was saying, on the website in notes for this lecture. So I will probably do it as fast as I can just to save time, because you really have to follow all the details if you really want to. So I have introduced the polar coordinates. So angle theta is angle from OX, and in this case my vector r, which has coordinates x and y, x would be equal to, let me put it as x of t, of time, would be equal to r of t times cosine of theta of t, right? So angle theta and the lengths from the origin of coordinates are function of t. So this would be my coordinates on the x, and coordinates on the y would be times sine of theta, right? This is x, this is y, this is r, this is theta. So it's a simple trigonometry. All right. Now, from this, we can actually have the equation of this type. So, the equation of this type would be equals. Now, x of t is r times cosine of theta, and r would cancel with the r cubed. It would be g m x, no, r cosine divided by r cubed, so it would be just cosine of theta divided by r squared, right? It's all function of t, obviously. Theta is also a function of t. So that's one equation, and the similar equation for the y. Okay. Now, what's also involved here, and that would help us significantly, is there is a concept of angular momentum. And angular momentum is very much related to torque of the force. But in this particular case, it's a central force, so it's always between object and the source of gravitation. There is no torque. So there is a law of conservation of angular momentum of object which is moving in the gravitational field. Now, this topic was addressed before, again in one of the previous lectures, and I will just use that angular momentum, which is equal to this. This is vector product, cross product of position and velocity. Now, these are function of time, but this is a constant. So this is a vector which is perpendicular to r and v. R and v define the plane where the whole motion is moving, which means L is perpendicular to it. That's what vector product is. So L is directed along the z-axis, and its value is, its magnitude is constant. Now, this is the preservation of the conservation of angular momentum. That's what it means. So I will use this function, this particular law, to basically get rid of r square, and you will see what happens actually here. Now, from this follows that L times L divided by L divided by M. Okay, and I would like to calculate this. So what is this? Again, R is my x and y. V is my x and y. Now, I can always express this in r cosine theta, r sine theta. And this is, now I have to take the derivative by time. Now, derivative by time is from the x-coordinate. Okay, that's a multiplication of two different functions of time. So it will be r prime times cosine theta minus r sine theta and theta prime, right? The derivative of product is the first derivative of the first time the second, plus derivative of the second, and from a cosine the derivative is minus sine, times inner functions derivative, because theta is itself function of t, of time. Now, if I will multiply these two vectors, now the third component is 0, obviously, the z component of r and v. If I will multiply them, what I will have is, and there is a law of multiplication, obviously, so you have the third coordinate is 0, third coordinate is 0, and you will multiply these three-dimensional vectors as a vector product, and the result would be, I will just skip all the intermediary calculations. The result would be, I will take it from here, it will be so this thing would be equal to r squared times theta prime. Why? Because whenever I will start multiplication, it should be this times this minus this times this, and all the sine square plus cosine square will give me 1. So all these cosine and sine will actually disappear, and the result would be this. And that actually is a very, very convenient thing, because we are very lucky that you can put 1 over r square equals to L divided by M and theta, no, it's M divided by L, right? It's M divided by L times theta, am I right? R square is equal, yeah, and I can put it here, you see, 1 over r square, and my result would be x second derivative by time is equal to G M divided by M L thetas and cosine of theta. By the way, M cancels out. Just a very quick note, why M is cancelling out, and it's not really a surprise. Remember experiment of Galileo did in Pisa with the Tower of Pisa. He dropped different objects and they came down to the ground with the same speed, with the same time actually. Now, if he will push horizontally something, the time would be the same to fall down, and the speed, if the speed will be the same, they will move along the same trajectory regardless of mass. So it's not surprise that M is cancelling out. If you have two different objects of different mass, but they are at the same position and at the same velocity in the very beginning, they will move along the same trajectory. Now, why is this such a good thing? Because this is a full derivative of sine of theta. What's the derivative of sine? Cosine times derivative of inner function, which is this. Actually, I forgot to put minus somewhere. Probably it would be here and here and here. But in any case, this is a full derivative, which means this is a derivative from the speed of the x component of the speed, of the velocity rather. And this is the full derivative. So I can integrate them. And my result of my integration will be integral of this would be this. The first derivative, which is basically the first component of the velocity, is equal to some coefficient. I'll put coefficient k, but with a minus sign, sine theta of t actually, plus some constant c1. Same thing would be for y, and it would be k cosine of theta plus c2. So this is a huge success, quite frankly, because I have already defined my velocity components as the function of theta only. Now, from this, I would like to come up with what's the r, what's the distance from the source of gravitation as a function of theta. Okay, this is another little trick. And again, all is described in the notes for this lecture in more details than I'm doing. Again, let's recall the formula that 1 over r square is equal to m over L times theta from the law of conservation of angular momentum. Okay? So, from this, we can compare actually this with expression of velocity. Okay, x is equal to, if x is equal r cosine, then prime is equal to r prime cosine theta minus r sine theta theta prime, right? And we can compare this one with this one. This is x prime, this is x prime. So these are equal to each other. So we have this particular equation, minus k sinus theta plus c1. And same thing with y. Y prime is equal to r prime sine plus r cosine theta, theta prime, and is equal to k cosine theta plus c2. Okay? So now, how can I get r from here? Very simple. I'll multiply this by sine of theta and this multiply by cosine of theta. And from this, I will subtract this. Now, r prime cosine sine, and this is sine cosine, will cancel out. Now, this would be, if I multiply it by cosine, that would be cosine square, and this would be sine square. I'm subtracting. So I will have, therefore, r times 1, basically, right, times theta square. I mean theta prime. And it's equal to, if I will multiply this by cosine, this by sine, and subtract, again, would be cosine square plus sine square would be k plus c2 minus c1, right? Am I right? Yeah. Right. So that's how I get k. That's how I get r times theta prime. Okay. From which theta prime is equal to whatever that okay. So I've got the expression for r from here, and what else did I get? How can I then get okay, what I know that r squared times theta is constant, right? It's L over m. And r times theta 1, theta prime is equal to this. So if I will divide one by another, I will have r is equal to Lm divided by k plus c2 minus c1. Am I right? Sorry, when I multiply by cosine, I have not just c2, I have c2 times cosine. And minus c1 times sine. Forgot. Same thing here. So cosine minus c1 sine. But again, k, c2 and c2, c1 and c2, they're all constants, and we know them. c1 and c2 can be defined very simply from these equations, because this is the first component. This is basically speed. If I will put speed, the first component of the velocity, the x component, it's known, and from this I will get theta at time is equal to 0, theta is equal to 0. So if I will put 0, it will be, this is 0, this is known thing, it's a velocity is x component at time 0, and that would be c1. And for c2, if theta is equal to 0, this is k plus c2. So this is the y component of the velocity, which is known thing, so it will be this y component of the velocity minus k would be equal to c2. So everything is basically defined. And this is the final result, basically. This is the formula. We can even simplify it slightly. Let me just do one more simplification, and that will be it. Because all we needed, as I was saying, we need the expression of distance r as a function of the angle theta. Okay, C2 cosine theta minus C1 sine theta is equal to square root of C1 plus C2. This is exercise in trigonometry which was covered in trigonometry course of the Unizor.com. So that would be cosine of theta times C2 over square root minus sine theta C1 square root. I can always find angle phi, where this would be cosine phi is equal to C2 divided by this square root, and sine phi would be equal to C1 divided by square root. And this square plus this square would be obviously 1, because the square root is C1 square plus C2 square. So, and what is this? If you substitute these, that would be cosine of theta plus phi. So instead of this, I can put some other coefficient, I don't know, q whatever, times cosine of theta plus phi. Well, now, why is it better? It's better because of very simple circumstance. If instead of OX as the basis for my polar coordinate, as a starting point where the angle is equal to 0, I will change by phi, and I know what phi actually is. If I will turn it by phi, then that would be just theta. So if I just change my coordinate system slightly by turning the whole thing by angle phi, my formula would be without the phi, obviously. It would be just some coordinate r would be equal to a divided by b plus c cosine of theta. And that would be my final formula. And this is definitely a curve of a second order, because that's what we were talking about in the previous lecture. So this is a general description of ellipse, hyperbola, and parabola. Depending on these constants, it would be one and another shape. That's it. So we have proven that it would be some kind of a second order curve, because that's the general polar coordinate description of all second order curves. And depending on this coefficient, it will be one or another curve. Read the notes for this lecture. Again, go to Unizor.com, Physics Plus for All, Laws of Newton, and Kepler's first law. That's a good lecture for, good written material for this lecture, because I might be a little bit faster, or I forgot minus sign or something. Now, the write-up is good, and I do recommend you to read it. Well, that's it. Thank you very much, and good luck.